Okay, so let's get started on how to solve an exponential problem with the aid of a logarithm. So before, when you're solving exponential problems, you would change the base and then drop the bases and then just work on the exponents places to solve the equation. Now, in most situations, you're not going to be able to do that. So this is how the logarithm comes into play. And just know that you have an advantage. When I was your age, we had something called log tables, and you can look up log tables on the internet. I still don't know how to use log tables. It was really frustrating. But now with the aid of a calculator, this log button right here, log log, is the inverse of base 10 raised to the x. I don't know if you can see that. Base 10 raised to the power of x. X is an exponent spot. A log undoes an exponent. So you guys have a distinct advantage. So here's the definition of a logarithm. The definition is for every a that is greater than 0 and b is greater than 0, then your log of base b of this argument a equals your exponent. And that is equivalent to the equation that says the argument is equal to base b raised to the power of x. So you will start off on this side looking at some solution or argument equal to a base raised to some exponent, turn it into this situation, and this piece is what you'll end up entering in a calculator, but for base 10, it will look like this on a calculator. All right, so let's get started. The first problem is 14 1/10 equals base 2 raised to some power x. This says that I have a base 2 raised to some exponent equals this value here. All I need to do is convert it to logarithmic form. Base, my log of base 2 of my argument, which is 14 1/10, equals my exponent. Now I'm going to introduce one more item here, okay? That is the fact that your calculators aren't often going to have base 2. They have a natural log, which is a base of e, is a transcendental number. We're not going to teach what that is right now, but log base e, log base e is also known as a natural log, ln. The log on your calculator is always going to be log base 10, and that looks like plain old log, okay? All right, so because my calculator won't do base 2, I need to change this up, and I can change this expression into log base 10, or just log of 14 1/10 over the same log with the same base, 10, argument 2 equals x. Now this is a workaround that allows you to use different bases, okay? So the easiest way to remember this is that you notice the subscript 2 is also the denominator. So it's sort of like 14 1/10 is the numerator, 2 is the denominator, and they're sharing the same base. You can use natural log or log base 10 to solve this problem. So in my calculator, I'm going to enter log of 14 and a tenth divided by log of 2, and I get 3.817 approximately. Let's call it approximately 3 and 82 hundredths. So we would write that as x is approximately 3 and 82 hundredths. Now to confirm that's the case, we can plug that value back in to the original problem. Is 2 raised to 3 and 82 hundredths approximately 14 and a tenth? The answer is yes. Next problem. It's always good to have these in your notes. The definition, log base b of an argument is equal to my exponent when the equivalent form is the argument is equal to the base raised to the exponent. So my next problem is 4 times 10 raised to a power of x equals 4,650. Okay. Using reverse order of operations, I need to undo part of this first before I evaluate or turn it into my equivalent form here. So divide both sides by 4, and I get 10 raised to the power of x equals 1162 and a half. I now have this form. My argument equals my base raised to the power of x. I turn it into logarithmic form. My log base 10 is going to be the basis on my calculator, so I'm just going to write log of my argument, how I put it in the calculator, is equal to my exponent. What I need to raise base 10 in order to get 1162 and a half. Approximately 3 and let's say 7 hundredths. Now we can test this now in here and see if that's the case. We'll actually use the whole thing. 4 times 10 raised to the 3 and 7 hundredths. 4 times 10 raised to the 3 and 7 hundredths. That's close. If I want to test this a little further and see if I can get a more accurate decimal, I will get closer to my 4650. But that is close enough